All right, 9 o'clock, 9:01 actually. So time for us to start. Today is our second day of week 6, fourth day of talking about linear programming. This will be the last day that we do that. I also plan to go over another 2 linear programming questions in the workshop this evening. I was also planning to do a fair bit of matrix stuff there, but my previous 2 sections, we didn't actually have time to talk about matrix, do the practice questions with matrix addition that I showed you last time, or talk about the scalar multiplication, matrix multiplication at all. Basically, we spent the whole time talking about a little bit about the midterm and then a whole lot about the linear programming example, the last big one. So that looks like where we're going to be spending our time, and the remaining little bit about matrices we will do, excuse me, in our next class on Tuesday next week. So that's where we'll have to find time for that. The matrix addition, scalar multiplication, the transpose stuff, matrix multiplication is going to be one of our midterm topics, but we'll be able to get that finished up by Tuesday next week. Okay, so the exam itself, I've shown you this in our previous class. So Monday evening, not next week, but 2 weeks or week and a half from now, please make sure you have that time available in the evening. We'll do 100, like the exam itself will be 2 hours, 120 minutes, but you'll need some time afterward for the scanning and before, just making sure your cameras and everything are set up. So we'll need some extra time there. I'm guessing you guys have heard already, but the schools had to delay the potential return to in-person classes. So when we have our exam, we will still be entirely online at that time. So nothing we can do about that. So we'll have to be doing an entirely online exam. It is overall similar to how we do the homework. It's handwritten, except, we're on Zoom, so you have your cameras and everything on. Some detail about that. I've already posted a big thing on the classroom page, which why don't I just quickly show you now. I'll give you the short version of it here. Likely a number of you have additional questions beyond that. I've addressed most, if not all, hopefully all of those questions on our classroom page here. So midterm preparation. Here's the date and the time and all of the stuff and the rules for it. Here's kind of the procedure, sort of what you're expected to do to get ready for this and how you have your cameras set up and stuff. Just to make sure you've done that correctly, I have a thing here where you're going to actually show me like the side view and the scanned pages and the file renaming and everything. Just make sure that you are able to do all of that. Those is graded. We will actually be considering this as a homework grade. So read the instructions, take the pictures, free points basically. Okay. The short version of it is this. You will be joining Zoom with 2 devices. So you have a front view, just like you can see with me right now, sort of probably the camera on the front of your laptop. And then a second side view camera, which probably your phone or a tablet or something. The side, so I mentioned a bit more about the side view in a moment. Scanning PDF, 1 file for all your pages, and you're taking a selfie with each page that you write, and then you're going to upload those 2 things to separate places. The separate places you can kind of see here, there's the part 1, part 2. So the scans and then the selfies you're uploading to different places. So we can track exactly when those things were submitted. Okay, little detail here. Side view will have to show this. So we see still like your face from the side, but we also see your monitor, and we can see where you are reading the questions so that we know you're not looking at some other websites, so you don't have like textbook files open or something. So we have to be able to see your monitor and then your desk. So we see that you don't have like notes sitting beside you and you're not using a calculator or whatever. So side view will look like this. Front view is just pretty typical front view. Scanning, we've talked about this a whole bunch of times, so don't need to repeat that. Selfies, that's the other thing. Where's my notebook? It's over there. So this is not a regular piece of paper, but it would be kind of like this. You're just going to hold the paper up in front of your face, take a selfie with it. This is how we guarantee that you personally have written all of the pages that you have submitted, and it wasn't just someone else sent you a file and you uploaded that. So also the selfies serve as a backup in case you're some problem with like one of your scanned pages or something, you accidentally cut something off. We can take a look at the selfies and sort of verify, or we know that that has been submitted on time by you during the exam. Otherwise, if there's a problem with your scans, I can't contact you 2 or 3 days later and say, well, show me what was cut off, because I can't guarantee that that was done during the exam time. So selfies are a backup for you as well. The writing on your papers should be visible in the selfie. If I zoom in, I should be able to see what everything is. If you can't see it right now in these photos, that's because I purposely blurred it out because I don't want you copying my answers for this practice homework. I want you doing your own, but you can read all the parts here, hopefully. Depending on how large your screen is, like you can clearly read my name there and a fake ID number here, question 1, question 2, like that. So the writing should be visible. All right, those are the big 3 things. The rest, as you may have noticed already on the classroom page, that whole procedure post, there's a lot of detail there. I think most of it is common sense, but all the same, please take some time to read through that and then submit the practice midterm stuff, just so you show me that you've found a place to put the side view camera and whatever, where everything's visible and that you're ready. Like right when the exam starts is and students have tried to do this in the past, like 2 minutes before the exam is scheduled to start, they're sending me like urgent emails about like, is my camera set up okay? That is way, way too late. Like right when the exam starts is the worst time to be asking me all that stuff, because there's like 140 people waiting to start. So this practice exam, this little homework thing here, that's how we know that everyone will be ready. Okay. You probably have more questions about that. If you do, I will gladly take some questions at the end of today's class with whatever extra time we have. Also, once you've gone through the process with the photos and you've read through all the testing procedure thing, you may have more questions. Okay, in our next class next week, we'll have time and we'll go through all those questions, whatever things you want to ask, make sure everyone understands the process there. So we'll have that time to go through all those questions, but right now I want to make sure we finish our linear programming example, because it's going to take a while. Linear programming is not quick. All right, review of some terms here: constraints, feasible region, corners, objective functions, ISO function lines, ISO profit lines, etc., best solutions, these kinds of terms that we have been using. Hopefully we have a decent memory of these things. So let's try to review. I've shown you this slide a few times with the process, but now you can see I've taken out a few parts. So can you try to fill in these gaps for me? We'll try to do this together. So first, step 1 for linear programming, you should identify what?
Variables.
Variables, okay. All right, so find the variables, find the things that are variable that you can use to represent everything in the problem. So we use those variables to make equations or inequalities for 2 things. Anyone? What do the inequalities represent? What do the equations represent?
Maybe for the objectives and constraints.
Okay, there we go. So I have them kind of in the opposite order here. So the inequalities are representing the constraints and the equations are representing the objectives. So we build the equations and the inequalities for these things. And then step 2 is to do what?
Graph.
All right, graph everything. Put it all on the graph and look at it. Get that visual representation of what it all looks like. Then from the graph, on the graph, we want to identify 2 things.
Feasible region and the corner.
Okay, good. So the feasible region, so our shaded in area that shows all the possible solutions, and then on that feasible region, what are the corners of it, the points of intersection that map out that feasible region? All right, and from there, we want to identify the corner that is something.
That's located like mostly closely to the ISO somewhat line.
Okay, the ISO whatever line.
ISO whatever line.
Yeah, so our ISO function line. So whatever our objective function is represented with that ISO function line, we want the corner that's closest to that. So corner closest to our objective function. So we will do that using, so an ISO function line that is close to, but something. This is harder to remember, but.
Parallel, perpendicular.
Perpendicular is how we are measuring which one is closest. We make the perpendicular lines. That's how we measure what's closest. Okay, yeah, this part is a little harder to remember. So an ISO function line that is close to, but outside the feasible region. If we've done that, then we just figure out which one is closest and that's it, we're done. All right, and we can find the exact coordinates by we solve for the point of intersection, whatever two constraints are meeting at this point of intersection that we care about, then, okay, we just a little bit of algebra, systems of equations, we can solve for that point of intersection very easily. That will give us the exact coordinates in case we can't read it right off our graph. If we do want to check our solution, maybe we have a second corner that is also pretty close and we're not 100% sure that maybe we have a hand-drawn graph and we're not 100% confident that we have the best corner, then maybe there's another one nearby And we just check 2 of them in the objective function to figure out which one has the highest profit or lowest cost or whatever. Also, if we think there's a possibility we've made a fairly large mistake, we could also take our solution and substitute that solution back into each of the constraints. This is constraints, equations, that should be inequalities. Put that back into the constraints and make sure it works, because the constraints are telling us what the limit on the problem is, how far, like we can't go past this point, or we have to be at least to this point. And excuse me, our solution should be within all of those constraints. That was the whole reason for making the constraints in the first place. You probably won't have a problem with that, but if you want to be very certain of your solution that it's valid, then that's a good way to check it. Okay, matrix stuff, I'm actually going to skip over because in the previous sections we didn't have time to review that, so we'll come back to that in the next class.
Trying to...
Sorry, someone, yeah, okay. All right, so review here. From last time we did the minimization problem, and we had this, we had the vitamin supplement stuff with this 2 different sort of some kind of liquid drop thing, supplement X, supplement Y. We want to find the cheapest way of combining these 2 supplements to get the minimum amount of vitamin C, vitamin D, vitamin E to meet each of these requirements, and then while minimizing our cost. So we had these 3 things here that were basically pushing our costs up. Like we can't just do 0 drops of the supplements, or we can't just do 1 of each, because then we wouldn't reach these daily minimum amounts for vitamin C and D and E. Okay, so we have these things forcing us to spend more money, pushing costs up. But despite all of that, we still want to find a way to have the minimum possible cost. And we made our constraints and we figured out our solution, our feasible region, and our best corner. And then we kind of zoomed in and we figured out that it was B here. And C was kind of close, but B was better. Okay, so that was our whole process last time. We're going to repeat that. So we'll have a larger problem with 3 different constraints, but as a maximization problem. And that's the whole focus for today's class. So I'll show you this, give you a moment to read it while I go fill up my water cup, which I forgot to do before class. So read this, and then we will see if we can identify variables and build our constraints and equations from this. All right, let's talk about the problem that we have here. So some company, they make 2 different types of metal gates, like fancy metal gates for gardens. to me, this is like a European thing, like people in big fancy houses who want to have like some big backyard garden and they have this fancy gate with like animals or whatever, like shapes of animals or something in it. Okay, whatever. Company makes a product, want these two things, fancy gates, basic gates. And we have a certain number of labor hours available. And we have prices and profits for this, trying to maximize revenue and profit. Okay. What things make sense to be the variables in this problem?
The number of each type of gate,
Okay, and why are those what you're choosing?
because by knowing the number, we can calculate the revenue and profit.
Okay, is that the only reason?
If you ask this question, then no.
Number, basic gates sold. And F, number of fancy gates. So these two variables, first of all, they are variable. They're things that are flexible in the problem. Like, can we change how many fancy gates we make? Can we change how many basic gates we make? Yes, those are flexible numbers. Those are variable. The other parts of the question here, for example, how many hours of welding does it take to make a fancy gate? Can we change that? No, we can't. How many hours of welding labor do we have available? Can we change that? No, we can't. That's set. So that's locked in. Those are constants. We can't change those things. That's part one. So find the thing that is actually flexible, the thing that can actually vary, as we heard. So we can use those variables to represent the profits and the revenue here. So these two variables, we can make an equation for revenue, make an equation for profit. So they represent our objectives. And the third part is they can also represent the constraints. So we have this limited amount of labor hours. Can we make an inequality using these variables to like represent each of these things? Yes, we can. So it is actually variable. We can talk about our objectives in terms of those variables, and we can talk about our constraints in terms of those same variables. So that's how we know they are the right things.
Excuse me, Professor. Why aren't we using X and Y as variables?
We can call them whatever we want. There's no reason that we have to use X and Y. In this case, it'll be just, I think, a little easier to remember. Like otherwise, we'd have to be trying to remember which one means, which one is the X and which one is the Y. You don't have to use X and Y. You can use whatever you want. So if we're doing this, one thing that we could add here, so since you've mentioned that, we could just add a little X here and say our horizontal axis, we will choose to put B on the horizontal axis, and we'll choose to put Y on the vertical axis. You notice that I've sort of switched the order of these, B first, then F. That's just because I've done this problem already, and with the size of my monitor here in my slides, that orientation fits much more nicely, so that's why I've done it that way. Okay, we have our variables. So now let's try to use those variables to actually build some, we'll do the inequalities first for our constraints and see if we can represent everything here. So constraints, can someone tell me a category for a constraint and then the actual inequality for it?
For the numbers of fancy gates and basic gates during the available hours. It's 6F plus 2B is equal to 840 hours.
6F plus 2B, I'm going to write those in the opposite order. 2B plus 6F is, you said less than or equal or greater than or equal?
Is equal to.
Equal to, you said, like this. Okay. All right. First, what does this represent? These aren't just random numbers. Where did you get this from?
During the given 840 hours, they are spending 6 hours for fancy gates during the welding process.
Is that,
And they spend 2
okay,
hours.
welding. So that's one of our constraints that we should be very clearly labeling what each of our things are representing. So for welding, these are the numbers. I don't like the equals part here. These are usually inequalities. So is it less than or equal or greater than or equal?
Less,
Why less?
because they can't use more hours than.
Okay, so this is the number of hours available, which is what the problem said. So, or is right here on the chart as well, hours available. So that means if we use fewer hours than that, that's fine. If we use exactly that many hours, that's fine. If we go over that, well, we don't have that many hours available. So we can't do that. In a business context, this is a very real world thing. So, you know, you have some sort of labor contract which says that you don't force your workers to do more, like because they're part of a union or something, or you've outsourced the welding and this is all that's available, or if they work more than this, we have to pay them overtime and that changes our profit and we don't want to do that, or whatever reason. So the word available itself means up to that much is okay and less than that is okay, but we can't go over. And we'll do the same thing for finishing. In case that's not clear, finishing B plus 2F less than or equal to 300. Finishing means like polishing, basically. The polishing and the sanding and just the making it look nice, painting maybe, that kind of thing. And admin work is B plus F and less than or equal to 250. So our three constraints, and we've labeled the categories for each of these things. So there we have our constraints. We have one more thing that we need to make, which are the objective functions here. Tell me what one of the objectives is and tell me how we could calculate it.
Profit.
What about profit?
It should be 55.
Profit. Go ahead.
Well, 6. Okay, so oh man.
Okay, keep thinking about it. Anyone else want to jump in?
55F plus 25B.
Okay, and I'm going to write that in the other order. Yeah. So 25B plus 55F, because B is number of basic gates sold. How much profit do we get from one basic gate? 25. So 25 times B gives us total profit from basic gates. Same thing for the fancy gates, and then add that together. There's the total profit for this kind of product. So what I wanted to have here is just maximize. I know profit, so of course we want to maximize it, but these problems, linear programming, it's not just about like dollars and such. We could have any sort of objective, like number of workers in the factory or something. We could want to maximize or minimize. It's good to just state very clearly we want to maximize profit. But we have a second objective as well.
maximize revenue.
Mhm. That's the other one, maximize revenue. And we can read that right off the chart as well. 95B plus 120F. So revenue selling price, the price that the customer pays, that times however many things you sell, that's your revenue. We gave that definition for revenue a while back when we did the break-even points. I'm just seeing in the chats about the less than or equal, I think is the question here. Hours available. So we just have to read the question and understand what that means. It does. So if we had to use exactly 840 hours, not less, not more, the problem would have said that like 840 labor hours must be used. It would have said something like this. But if it's available, then okay, that many or less than that much is okay. So just sort of how we usually interpret these words, but then also we can think of just the practical real world context of this problem and think which one makes more sense. And that's how we can figure it out. So that's part of the problem, trying to figure out if we are, for our constraints, are they less than or greater than? Okay, so that's the setup here. And I have this on my next slide typed out for us. So just clearly labeling, the B is the one that we're going to put on our X, like our horizontal axis, the one that's usually X, and we'll put the other one on the Y. We have our two objectives here, and just adding in these non-negativity constraints because we can't make or sell a negative number of either of these gates. So both of these must be 0 or greater than 0. They cannot be less than 0. Okay, so we've taken the word problem, we've turned it into math. So now that was step 1. So now we get to graph everything. Okay, and using the same graphing approach that we've done for the previous questions, where we have it in standard form and we just find the two intercepts. Let's do the first one, welding. Can someone tell me what these two intercepts would be?
420.
Mm-hmm.
And
140.
140. So it's a 2 and a 6. So 840 divided by 2 gives us 420. And then just divide that by another 3 to get 140 here. Okay, so the other ones are pretty simple. I'll just write these in for us. So 300 here, 150 here, 250 and 250. And then we'll just put those on our graph. All right, welding is B 420 here and F 140 about here. Finishing 300, 150, and then admin 250, 250. Are we shading above or below these lines?
Below.
Below all of them, because they're all less than or equal. So this here and then everything below represents our feasible region. How many corners do you see on this shape? And where are they?
4.
Okay, tell me some of the corners.
The one on the F intercept, F axis.
F.
The orange, the orange one.
Okay, orange and our F axis here. Next one.
Interception of the purple and the orange line.
Okay, orange and purple. Just slight terminology thing. The intercepts are usually with the axes, but just two lines not on the axes are intersections. Just it's easy for us to get those two things confused. I just want to be very
Sorry.
clear about the terms. That's all right. Next one.
The same thing with the blue and the purple lines.
Okay, so this intersection.
And 300 be aces.
Not
Oh,
the-
sorry,
250.
250. Sorry,
the
sorry.
250, this one here, this intercept here. Okay, so those are the four corners. Once we've shaded in our shape, it's pretty easy to just kind of see those corners, but again, we have to remember those are the points. Our best solution is one of those four. So let's put these on here, there. Okay. So here's the nicer looking version of it. And I've labeled these four corners, A, B, C, and D. We have our nice little labels on the graph for each of our things. Okay. We kind of skipped the step where we graphed the objective functions. So let's do that now. Let's go back to that. So we need to choose constants. In our previous problems, the previous questions we solved, it was kind of easy or relatively easy to just kind of find a number that works out cleanly, where we just look at our two coefficients and then multiply them together or something. And we were able to pull out a number and it wasn't too hard. In this case, it doesn't look like that will work out quite as nicely, or that multiplication wouldn't be quite as easy. So again, on the homework questions, exam questions, the numbers will work out reasonably well. You will not need to use a calculator for this, for them. But in some real world context, if you're actually doing this analysis for some business, then real world doesn't follow those rules. The numbers could be anything at all. So let's just choose a number and we'll kind of cheat, and you guys can punch it into some calculators and tell me what the results will be. And then we'll see how those numbers work out and adjust as needed. So the number I chose on the next slide here was just 30,000. I wasn't really sure. Revenue here, maybe it's going to be a lot more than this or a lot less. I just kind of took a look at the numbers and just kind of made an educated guess. The slope of these iso function lines is the thing that we really care about. So that's why it's okay for us to just kind of just make up a number and then see how it works out, because we can always just choose a new constant and then slide that line up and down however needed. Excuse me, throat's very dry today for some reason. So for 30,000, can you guys tell me what the B intercept and F intercepts would be?
$315.8.
Okay, 315.8 and then ... more decimals. And our F intercept?
250.
Okay, well, that one works out very cleanly. That's nice. 250. 315.8 something. Okay, we had to use a calculator for that. So our question now is this a good number? Is this 30,000? Is this going to work? Is this useful for us? Is it way too small, way too big? The way we can tell this is by looking at the intercepts, the other intercepts. So our largest B intercept, our smallest, 420, 250. For the F intercepts, also our smallest, our largest. it's in that range. It's close to the other intercept, so it'll probably be at least somewhat useful for us. Maybe not the perfect number, but it's not going to be so small that it's just a little tiny thing in the corner. It's not going to be so big that it's like way over here and doesn't help us. It's going to be kind of close to the constraint line, so seems like a good place to start. I know that feels very like sort of soft or mushy, whereas math is typically like very, it's like precise. But again, we can change the constant later. So let's just put that on our graph and see what we get. Those parts there. So there's the ISO revenue line for 30,000. So that's the constant. It's not the perfect line, but we can get some information from this at least. So we have 4 corners, A, B, C, D, and can we eliminate any of these? Are there any that we know right now are definitely not going to be the best solution?
Yeah,
Two
A
corner.
and D.
Sorry, A and
D.
B.
D.
B.
okay. Well, why do you say D? And then we'll hear the other person and what they say about B.
Yeah, maybe I changed my mind. B. We can eliminate B because D seems more closer.
Okay, so remember we are finding the perpendicular distance, the shortest perpendicular distance from the ISO function line, ISO revenue line here to these points. And which one of these is the shortest? Well, C and D, maybe right now we think those are pretty similar, but A and B, definitely not. Those are clearly a lot further away. So we can eliminate those two. So for revenue, it's going to be C or it's going to be D. Right now, we are just, we're not 100% certain. Okay, so I've chosen these numbers specifically to kind of help you see what can happen if we don't just, you know, the earlier examples, we just kind of like magically chose the perfect constants for these. So here we're going to see what happens when it's not quite so perfect and it gets a little messier, but you know, we can still figure it out. So not A, not B, it'll be C or D. Now, which one of those two? We'll come back to this in a moment. For now, let's switch over to profit, see if we can, maybe we'll get an easier solution for a profit. So similarly, 25, 55, not really seeing a nice clean way where the math would work out there. That's easy to calculate. So instead, I just chose a number of 10,000 here. So 10,000, and then just to skip the step of telling you guys to type it into your calculators, I've just put that on our graph. One of the intercepts is 400, and then the other one was here, it was 178 or so. But I think we've done enough practice with finding the intercepts and graphing based on that. So I'll trust that you guys are okay with that part. So here's this profit line, our ISO profit line, which I put in gray just to give us some variety and just make it separate from our ISO revenue line. So it looks like this. And once again, we have our 1, 2, 3, 4 corners. Right now, is there any corner that you can identify as definitely not the solution?
D.
D.
D. Okay, everyone's saying D. So the other 3, A, B, C, right now, they look pretty similar. They all look pretty close. It's kind of hard to tell which one of those is going to be closer or further away. So profit line, 10,000 was reasonably close. We can make a good guess of how we should adjust the number. We've eliminated one of the possibilities, but not we're not down to just one here. So profit also did not work out super cleanly. That's okay. We'll just take our numbers and adjust them down a little bit to just slide the line closer and see what we can get there. All right, so that's just trying to remember what we have. Okay. All right, so first just zooming in. Haven't changed anything yet. I just zoomed in so we can put our lines a little closer and be able to see it more accurately. You know, if you're doing this on paper, you don't zoom in, obviously, maybe, I don't know, just lean closer to hold your paper closer to your face. So 30,000 and 10,000 here are the two constants that we had, but they didn't quite work. So all we're going to do is just adjust those numbers down. We want to move closer to this region. So we'll just adjust the numbers down and graph those and see what happens. So instead of 30,000, I chose a number. Let's just drop it down by 5,000. And sorry, here's the 30,000 line. We'll drop it down by 5,000. And 25,000, again, skipping the step of calculating the intercepts. We'll just, I've done that for us here. And this is where the line looks like. This is what the line looks like when we have this constant of 25,000. Remember, C or D, it was one of these two.
C.
Okay, so now, all right, C. It looks pretty clearly like the solution is going to be C, and D is close, but at this point, C looks like it's touching. It might even be the case that we somehow, just by chance, chose exactly the actual maximum profit, and then that's why it is touching at point C. But we can't be certain about that yet. We'll do our algebra and stuff to verify that, but C is closer than D at this point. So that becomes clear. Okay, so revenue, we figured out that it is point C. I'll just repeat the thing that I said in our previous classes, where if you're doing this on paper and you had a ruler, and if you're confident that your lines are correct, then we could just actually just take our ruler and just actually, you know, slide the ruler over and see what it would touch first. Or use the ruler to just draw additional lines if you're confident you can do that accurately. If we kept sliding it closer, we could see with this particular slope, it would touch point C first here. Okay, so that's just another technique. Right, so let's do the same thing for our profits line. We had profit of 10,000, our constant of 10,000, but that was too big. So let's adjust that one. I chose a profit of 8,000, just whole numbers, seems like another reasonable choice. And, you know, calculate the intercepts, skipping that step here. This is what the graph would look like for this. Intercept of about 320 and then about 143 or 144 or so on the F-intercept. Okay, so for profits, we were asking, well, or we are wondering, is it A or is it B or is it C? Now, this is another example of a kind of messy number where we wanted our function, our objective function, our ISO function line to be close to, but not actually touching our feasible region here. But in this case, our number is a little too low and it's actually inside. We can see it's actually going inside our feasible region a little bit here near point B. Okay, so kind of a messy choice, but if we do our logic correctly, or if we understands the idea behind these ISO function lines, then we don't need to choose a different number. We can use this to answer the question. So A, B, or C, which one is the best choice?
B,
Why?
because it's the, I think it's the closest one to the ISO profit line. Even if you, like, for example, this one is inside the feasible region, right? But if you slide it outside a little bit, it would still be point B.
Okay, so if you slide it outside, it would be the closest. That's the key part here. So let's say I chose a different number of maybe 7,900, 7,800 or something. It's possible that my ISO profit line would look like this green one I've drawn on the graph. And it would actually be maybe like touching point A or point C, but point B would be above it and outside of, or yes, above it somewhere. So it's not just simply the closest point, because if we think that, then we could say, well, it's point A because, well, it looks like it's touching. Maybe we chose a number that was way too small and our line, our ISO profit line was like this. And okay, it's touching point D, D is the closest, it must be D. But no, that doesn't quite work. So this is the, I'll re-ask the question that I asked. I can't do that. Okay. I'll re-ask the question that I asked last week. In what direction does the profit increase?
Perpendicular,
Diagonal.
All right.
like diagonal, yeah.
Yeah.
So this diagonal line perpendicular to whatever the slope is of that objective function. So perpendicular to this profit line that goes up in this direction. So point A, now understanding that, we can say this gray line represents all the ways of getting a profit of exactly 8,000. Point A is slightly below. So point A is a profit somewhere a little bit below 8,000. Point C is also below that line. It must be a profit of below 8,000. Point B is very close, but slightly above. So that must be a profit of slightly above 8,000. So A and C are below the line, below 8,000. B is somewhere above. B is clearly the better choice. It's the only one that's above the line here. So even if we kind of choose a number that's too small and we make this objective function that's actually inside our feasible region, we can still figure out our solution from that as long as we can figure out which one is the higher points, quote unquote, higher, relative to these arrows, perpendicular to our ISO profit line or our objective function. Okay, if that doesn't work for you, if that part's too confusing, then as Vincent said, we could just take our ISO function line, slide it slightly outside until it is outside, and then see which is the closer corner. I did that a little bit ago, and we could see that it was B. But we don't need to do that if we have a good understanding of this whole increases in perpendicular direction concept. All right, so that's lots of kind of explanation, background stuff. But basically, point C for revenue and point B for profits. Please note here that we had two different objectives, and then the solutions are two different points. There's nothing about the problem that says that the solution, the highest profit and the highest revenue will happen in the same way. And we can see very clearly here, we got different solutions. So in theory or in practice, if we have multiple objectives, we have to evaluate each one individually, figure out the best revenue point totally independently and separately from how we figure out the best profit. They could end up being the same points, but there's no automatic assumption that that will happen. If you have multiple objectives, you need to figure out each of them separately. Okay, let's just do our little, we need to figure out what these points are, and then we can go to the last part of this problem. Point C, highest revenue. What are the coordinates of point C?
$250 and $50.
250 and 50.
I guess so, yeah.
This is point C. Follow the axis down.
250. Yeah.
Yeah, so 200, pause, and 50, like
Yes.
as separate numbers. Yeah. Okay. So yeah, it's a little confusing to say those. So 200, comma, 50. So we can read the 200 pretty cleanly off our graph here. The 50, it also looks like it's right in the middle, all the way over here to 50. But also we can look at our constraints. We have this admin constraint that says B plus F must be equal to 250, equals because we are exactly on the blue line there. So if B is 200, so 200 plus F is 250, okay, F is 50. Like using the constraints, if we know one of the points, we can pretty easily figure out what the other one of the coordinates, we can easily figure out the other one. For point B, what are the coordinates there?
60 and 120.
60 and 120. And it looks like we can just read that off our graph. If we wanted to, we could just do systems of equations with welding and finishing, the purple and the orange, because that's what meets at this point. And then figure out, here's the B, here's the F. They are 60 and 120. So I'll sort of skip that step. I think we know how to do systems of equations at this point. Okay, so there are the coordinates for these 2 points. So our maximum revenue is happening at points 200, 50, and maximum profit is happening at 60, 120. And I've written out here also what the constraints are. So revenue is happening at admin and finishing. It was the blue and the purple lines. Excuse me. And then maximum profit was happening at finishing and welding, the orange and purple lines. Okay. How do we actually calculate the maximum revenue here?
We just put the coordinates in our equation.
Right, so 200 is B and 50 is F. So 95 times 200 plus 120 times 50. And what does that equal?
19,000.
19,000 for the first part. And
6,000 for the second.
6, so that's 25,000. So it looks like the constant that we chose for that revenue function, we just chose 25,000 because it seemed like a nice round number. And it turned out that that was actually exactly what the maximum revenue was. So, but now we verified that with this whole algebra process, the exact coordinates and then maximum revenue. So now we know that that second green line was actually perfectly touching at point C at revenue of 25,000. All right, and we can do the same thing on the other side to get our maximum profits. I think I just, yes, have this on the next slide here. Just kind of skip ahead to that. So 8,100. All right, there's the maximum revenue, there's the maximum profits. That first part is done, but we have one more thing here. This is the extension. This problem asked us to find unused labor hours. Find unused labor hours. Do you think that's possible? Is that something we could figure out in this problem?
Yes.
How might we do that?
That
Uh,
blue line,
I'll say just substitute the coordinates that we found into the inequalities.
Okay. All right, so these coordinates, so let's start with revenue. So revenue, we said maximum revenue happens when B is 200, F is 50, 200 basic gates, 50 fancy gates. We also said that that location is the intersection of admin and finishing. Admin and finishing. So if we take these numbers and we substitute them into this admin, not quite the constraint here, but just sort of the left side. How many actual admin hours do we need? Can someone tell us?
Exactly 250.
Yeah, exactly 250, because 200 plus 50 is 250. So actual needed admin hours was 250. And this is exactly what we should expect, because our solution says, like, we are on the constraint line for admin, so admin labor. So we are using all of the available admin labor. So that should be kind of, maxed out. So it should be 250. If we do the same thing and put this into finishing, we can see, okay, it's going to be 200 plus 2 times 50, that's 300. Okay, so this solution requires 300 hours of finishing, exactly 300 hours of finishing labor. So, okay, again, our solution was the intersection of admin and finishing, so that's exactly what we expect. Welding. Welding is the one that's going to be a little different. How many actual welding hours do we need for the solution?
300.
700.
700. So I'm going to write that out here. So it's 2 times B, and B is 200, plus 6 times F, and F was 50. So just these coordinates, the 200 comma 50, into our welding, the left side here, 2B plus 6F, substitute in the numbers. And our solution for maximizing revenue only requires 700 hours of welding labor. Okay, so how many unused welding hours do we have?
140.
140, just we have 840 available, and we only needed 700. 840 minus 700, some easy math there, 140. There are the unused labor, unused welding hours. And no unused hours for finishing and admin. So 0 for the other two, but for welding, 140 hours extra. That's a pretty important result. So we have, if we want to maximize revenue and maybe not profit because we want to maximize cash flow or something, then, okay, here's how we maximize revenue. And when we do that, we want to, have as much as whatever available to try to maximize revenue. But it turns out we kind of over-plan for welding. We have more welding available than necessary, so we can sort of reduce that a little bit. The problem hasn't told us, but let's say these numbers seem like it's the number of gates that they can make in maybe 1 month. So this is their monthly production numbers. 140 labor hours per month. A full-time worker does about 160 hours per month. So that's almost a whole person, like an entire full-time employee, the whole wages and benefits and insurance and all this stuff, like an entire person that we could let go from our company. So lay them off or retrain them to become a finisher or whatever. But that's a major potential, that's a major actual sort of waste here that isn't needed. So not only do we become more efficient with do we find the best way to maximize our revenue, we can also eliminate other sort of wastes or inefficiencies sort of connected with that. It turns out finishing and admin are the real kind of key things that are limiting our solution. But welding, we got lots of extra. We can cut that down a little bit. Okay, so that's just looking at the numbers here. Let's do that same discussion, but looking at our graph, which will maybe make it a little clearer. Right. So point C maximizes revenue. Let's do a different color. Point C maximizes our revenue. And again, our blue admin line here, this is the inequality. It's less than or equal to that. And the purple inequality was less than or equal to that, like this. So C is at the edge of those. It's at the very edge. So if it's less than or equal to 300, okay, C is exactly 300. Blue one is less than or equal to 250. Okay, point C is at exactly 250. So because it's at the intersection of admin and finishing, those two are maxed out. Those are, we've used all that's available. There's a term here, we call these two, finishing and admin are, and I have this written out on the next slide, tight constraints, because there's no extra available. And we can see that very clearly from the graph here. So no extra available, tight constraints. Imagine like you're pulling a rope, but now it's tight. There's no more that you can pull. We are at the limit of those two. So tight constraints. The other one though, we see for the for welding, there's a gap here. Remember, this is an inequality. This is less than or equal to 840. C is just somewhere down in the middle of that inequality. It's not actually at the limit. It's not at the edge of the orange line. So C is therefore not using all of the 840 hours available. How much waste is there? Well, that much. Exactly the length of that line basically is representing it. A larger distance means more waste relative to the total available. So welding is what we call a slack constraint. Slack means when you have a rope or something and you could pull it more. There is more available that has not yet been used. That's the concept with slack. So it's a slack constraint. There's more available that we haven't used. So looking at the graph, we can just kind of immediately see that that's true. So blue and purple are at the max. Those are the tight constraints. And where do we have extra? Well, it's welding, because C is not touching the welding line there. It's not at the edge.
Professor, can I ask a question?
Sure.
When we were calculating and used labor hours for welding, we put 200 and we also put 50 in the equation.
Mm-hmm.
How did you figure out that we should put these exact numbers?
Because
why not 60 and 120?
Okay, because C, the coordinates for C are 200, 50. and C is for revenue. So we were just talking about revenue now. We'll do B next, which is 6120. We'll do that next, but that's going to have a different slack thing because it's a different point. So we did 200, 50 because that's the maximum. That is the way to maximize revenue. So just because those are the location, that's the location, that those are the coordinates for C.
Okay, thank you.
Okay, and we'll do the same thing for our profits. Go a little quicker this time. So B, remember the location here for B is 6120. So B is at the intersection of orange and purple. So orange and purple will be maxed out. It will, point B uses exactly 840 welding hours, exactly 300 finishing hours, but admin, it is below the admin line. So that is where we have the extra. That is the slack constraint. So how much is it slack by? So B is, again, 60, 120. How many admin labor hours do we require for point B?
180.
180, because it's B plus F, and just 60 plus 120, that's 180. So point B requires 180 admin hours, but we have 250 available. So 250 minus 180, 70 unused or unneeded admin labor hours, where we have just someone sitting in the office playing games on their computer because they're bored and they don't have any work to do. So 170 hours, sorry, 70 hours, that's a part-timer, or we can reduce a full-time person to part-time, or lay off a part-time person, or if we're a good boss, send them to work on some other project or something. But that's a major amount of unneeded labor for this part of the business or this factory or whatever.
So
Okay.
when we calculate unused labor hours, we do it separately for each point.
Yes. So that's, yeah, this question was a little more confusing because we had two different objectives, but unused labor hours and the tight and slack constraints are also independent for each objective that we have. So for maximizing revenue, this is how we maximize revenue, B200 F50. When we do that, we use all of the finishing and admin labor available, and we do not use all of the welding labor available, which there. So by 140 extra. And then for the other one, for profits, we have our maximized profit is 60B 120F. Profit will be 8,100. And then we use welding and finishing. Those are the tight constraints. We use all that's available, but we don't use all of the admin available, and specifically this much, 70 extra. So all of those parts of the solutions are independent. If we have multiple objectives, each of those things need to be determined separately. Okay. All right, that was the largest linear programming question that we are going to look at, and we've added some new wrinkles here where we could have multiple objectives to consider. We also want to figure out any potential waste or unneeded resource, in this case, unused labor hours, and our ISO function lines and the constants we chose, the results were kind of a little messy and we had to think a little deeper to interpret them correctly. So it's a little harder in a few different ways, but still solvable. Okay, does anyone have questions about this example? Okay, so we will finish with this part here. There's an entire hour for this one linear programming question. These are not, as I mentioned, these are not quick. I have another 2 planned to go through in the workshop this evening. We should be able to get through both of those. I think we'll have enough time for them. We'll do a little bit of some matrix practice stuff in the beginning of the workshop, but we haven't really gotten too far with that, so not too much. We'll have to do more matrix practice next week as well. Right, I do have some kind of summary notes and stuff to mention about linear programming, but we are over time already, so I will save these for next time. All this lovely fun matrix stuff, which we didn't have time to get through. Matrix multiplication. Okay. So big maximization problem with linear programming. We can do that as well, even if we have some extra kind of wrinkles or challenges to work through. The practice questions for this are here, these ones in our textbook. I've done some of these. I did one of these in the workshop last week. We'll do another 2 of these in the workshop this week, today. And one of these is also your homework question. I listed that in Tuesday's class. I put that in. I didn't post it on the classroom page because some of the other students in the other sections, they had the holiday and I use this as like a makeup kind of thing. Don't worry about it. Just you can watch the video if you missed that. Those are the questions. I removed one of the questions, the one about matrix multiplication, from the homework because we didn't have time to talk about it in class and it's kind of confusing. And I could see from the preview homework I gave you a bunch of it's not intuitive. So we haven't done it in class, so it's not fair to make it homework yet. So homework is a little bit smaller than what I mentioned in that video, but I've written a note about that on the classroom page. Homework for this week. So week 5, 6 homework, that's up already. And this practice midterm thing, just read this, take some photos, rename the file properly, upload it here to the correct locations. There is going to be a homework grade for this. It's due by Monday, end of Monday. So do that and you get some free points that will help you out on the midterm. Okay, long class. If you have questions, hang around and ask after class. Otherwise, enjoy the rest of your day and your weekend, and I will see you all on Tuesday for some review. Goodbye.
Thank you very much, Professor. Bye-bye.
Bye.
Thank you. Goodbye.